Hello. In this lesson, we're going to be looking at radiation, what different types are there, and how do they interact with matter. Now, the two different types we're going to be looking at are electromagnetic radiation, which for the most part are photons, but we're also going to be looking at three different types of particle radiation. We're going to be looking at ions, which are just sort of nuclei with their atoms stripped off. We're going to be looking at beta particles, both positive and negative, so electrons and positrons. We're also going to be looking at, of course, neutrons. Now, photons, for the most part in this course, I'm going to refer to their energies in terms of electron volts. But this is not the only way that you can describe a photon's energy. You can also use its wavelength or its frequency. Now, I'm not going to do this. I don't really like to do these conversions back and forth. And for me, since most of the charged particle energies we're going to be looking at are going to be in terms of electron volts, that's what I'm going to make the photons, because otherwise I'm going to be, swapping back and forth and having to do calculation after calculation, and nobody's got time for that. But just so you're aware, if you do see a photon given in terms of its frequency or its wavelength, you can convert it into electron volts. Now, the electromagnetic spectrum, I assume that most of you have probably seen a diagram very similar to this at some point, probably in high school. All this does is show what energies correspond to what different types of photons. So all the way at the low end, we have radio frequency, moving in through microwave, infrared, visible light, UV, and then into soft X-rays, hard X-rays, and then gamma rays. Just one thing to note. X-rays and gamma rays can have identical energies. You can have X-rays that go all the way up into the hundreds of MeV range. It's just normally on these charts, they are separated, but be aware that they don't necessarily have to be. They can, in fact, have exactly the same energy. So, X-rays. Why are they even called X-rays, and why are they different from gamma rays? Well, it's actually pretty straightforward. It's how are they produced. If it's an interaction with an atomic electron, then it's called an X-ray. If it's a radioactive decay, then it's called a gamma ray. We're going to look at radioactive decay here in just a minute. So, there are two different mechanisms by which we can produce X-rays. The first is something called the characteristic X-ray. And it's basically a photon can come in, it smacks off an electron, so it leaves a hole or a vacancy in the electron shell. Then a higher shell electron, or one that's further away from the nucleus, can drop down into that hole. Now, the electrons that are closer to the nucleus have less energy because they're bound more tightly than electrons farther away from the nucleus. So if you go from an outer shell to an inner shell, that electron now has to lose whatever that energy difference is between those shells. And it does this by emitting emitting a photon. If you kick off one of the electrons that's very, very close to the nucleus, as close as you can get, which is the K shell, and then you're dropping an electron in it from one of the furthest away shells, it can be a significant amount of energy that now has to be radiated as a photon. These are X-rays, and we call them characteristic X-rays because the higher energy ones basically are taking the furthest away electron, dropping into a hole in the K shell or closest to the nucleus, and it produces a very specific energy that is characteristic of that nucleus, hence the name characteristic X-rays. Now, on the other hand, we have bremsstrahlung. Now, bremsstrahlung is not caused by a direct interaction with shells around a nucleus. However, they are caused by an electron having its path bent around the strong positive charge of a nucleus. Now, when an electron changes its path, it undergoes this curvature. It undergoes something called radial acceleration. Now, that would mean that the electron would have to gain some energy. But that really can't happen, right? It's not going to all of a sudden start going faster. So instead, what happens is that somewhere along the curvature of this path, that extra energy is getting dumped into the creation of a photon. And this is called a bremsstrahlung X-ray. And the more extreme the bending of the path of the electron, the more of its energy, or the more energy is going to be released in the form of this bremsstrahlung X-ray. Now, the characteristic X-rays are generally speaking low energy, KeV, low KeV. Although once we start talking about uranium and plutonium, they can get significantly higher into the tens of KeV. In fact, I think K shell for uranium is something like 80 KeV for that characteristic X-ray. So that's pretty much X-rays. It's, again, that's how they're produced, and that's what differentiates them from gamma rays. Now, speaking of gamma rays, I did say that they came from radioactive decay. Now, if we remember back in the lesson on the table of nuclides, which is sort of what we're looking here, everything that's not gray is a radioactive material that is at some point going to undergo radioactive decay, be it beta decay or alpha decay or even spontaneous fission. Now, most of the naturally occurring elements are in fact stable. They don't undergo radioactive decay, or if they do, it's on a ridiculously long time scale. Like uranium-238, I think it's, and we'll talk about half-lives here in 1 second, its half-life is something on the order of billions of years, which is why we still have it. And it kind of makes sense because any element which has a short, relatively speaking, half-life, we would never find it naturally occurring. Something like plutonium. Now, we make plutonium, so it is an element, and at one point it probably was naturally occurring, but on the time scale of like the age of the Earth, it's quite short, 94,000 years or something like that. So by the time, that it may have been present back when the Earth formed, moving up to today, it would have just completely decayed away. So radioactive decay can be characterized by kind of a single parameter, and that single parameter is the decay constant. All this is a measure of how much of a radioactive, how many radioactive nuclei of the same type are going to be left after some certain amount of time. Now, probably what you're familiar with is something called the half-life, and the half-life is related to the decay constant. It's related to decay constant by that formula there at the fifth bullet down, where you have the decay constant being equal to the natural log of 2 divided by the half-life, or if you flop it around, the half-life is equal to ln of 2 over the decay constant. So if we want to do the straight up calculation for how many atoms of a radioactive material are going to be left after a certain amount of time, we can use the top formula, where A is the number that you end up with, A0 or A0 is the number that you started with. The decay constant is specific to that radioisotope, and then of course T is the amount of time that has passed. So if I were to give you a decay constant and some amount of time, you could tell me how many nuclei are going to be left, or what fraction of nuclei are going to be left after that time has elapsed. Now the half-life it's a bit simpler, and it's just saying, okay, I know how many I want to be gone. How long is it going to take? So that half-life is just a manipulation of that top equation, and it results in something like saying, okay, well, I start off with X number of nuclei. I know for a fact after this time t, half of them will be left. I don't have to calculate it or anything. It's already done for me. So that's the difference between decay constant and half-life. And this is how radioactive materials end up just sort of going away the longer time has elapsed between when it was created and when we're looking at it. Oh, one last thing. Activity is basically how many radioactive decays of a particular material or a particular isotope are occurring per second, right? So the unit to this is a becquerel, and a becquerel is just one decay that occurs in 1 second. Now the international system of units, or the SI unit for this, is called the Curie, and it's a massive number. It is 3.7 times 10 to the 10th decays per second. So when you hear somebody talk about how radioactive something is, they're referring to its activity, and they're going to usually give it in, unless it's very weak, They're going to give it in terms of Curies. So another way to think about activity is how many photons or alpha particles or electrons or whatever the decay mechanism, how many of those are being produced per second. So when you start getting up into Curie level territories, you can get stuff that's really hazardous to be around because it's outputting like 10 to the 10th gamma photons per second. Those gamma photons are going to deposit their energy, and if you're holding it, well, it's going to deposit its energy in you, and bad things are going to happen, which we're going to find out later when we talk about prompt and delayed radiation and their effects on both things and people. Now, when we talk about fission in the next lecture, we're going to see that fission fragments, which occur naturally via the fission process, they're, for the most part, they're unstable. So they will undergo radioactive decay. But that's not the end of the story, and it's what makes fission fragments sometimes very, frightening and one of the worst aspects of the fission process. Because not only are those two fission fragments each going to decay and produce some kind of radiation, but then those are then going to decay, producing more radiation, and then so on until they hit a stable nucleus, which is not going to undergo further decay. In this particular example that we have up here, we have bromine and lanthanum fission fragments undergoing quite extensive decay chains, where we have 5 different decays from bromine down to zirconium on the left-hand side. On the right-hand side, we're starting with lanthanum, which undergoes 4 different decays to end up as being stable cerium. So fission fragments, it's not just what they're going to do, but what they're producing is also going to do, which makes them particularly dangerous. And again, we'll see this later when we talk about prompt and residual radiation. Okay, particle interactions. Heavy charged particles, as they move through matter, they're mostly going to see atomic electrons, right? And they're going to interact via the Coulombic force. Now, the issue with this is that the heavy charged particles, because they have so much mass, their momentum going in any one direction isn't really affected a lot by the Coulombic force exerted by these atomic electrons. So because of this, heavy charged particles tend to travel in a straight line. And then what they end up doing is that they keep most of their energy right up until the very end, when they hit a certain threshold where that momentum that they have isn't enough to stop the energy transfer via the Coulombic force to these atomic electrons. And once they hit that critical point, they slow down very rapidly, but still in a straight line. Now, there is a term called stopping power, and it's a measure of basically how far is a charged particle going to penetrate into a given material. And the units to this are energy lost per distance, or it could be energy loss per mass, depending on what particular material parameters you have. So, for instance, if I shoot a helium nucleus at, say, a layer of skin, it's not going to go very far. It's going to go microns at the most. So I can characterize how far it's going to get into a layer of skin by looking up, well, what's the stopping power of skin for a given energy alpha particle? And I can look that up, and it can be calculated, and I'll most likely have it in terms of MeV if it's a high energy alpha, or keV if it's a lower energy alpha, per micron, or millimeter for other particles, depending on how far they're going to penetrate on average. But the really distinguishing thing between a heavy charged particle and what we're about to see with electrons is heavy charged particles, they just keep going straight. So you don't get any bremsstrahlung or that additional radiation production out of a heavy charged particle. Electrons, on the other hand, they can be very affected by the interactions with atomic electrons, because their momentum's not nearly as high. Their mass is very similar to those, or it's the same as the atomic electrons they're interacting with. So electrons tend to have their path deflected quite a bit. Now, if we look at this sort of tortuous path here on the screen, this is very sort of characteristic of an electron traversing a material. Now, every time you see these major path changes, this is an electron interacting with a nucleus instead of these atomic electrons. And when it interacts with a nucleus, depending on how much charge is concentrated in that nucleus, the electron can undergo extreme path deviations. Now, when this happens, the electron undergoes something called radial acceleration. Now, it really is not supposed to gain energy. I mean, again, it's a little more complicated than this, but you can kind of think about it in this way. So the electron undergoes radial acceleration, which means the energy is increased, but it can't increase its kinetic energy. So that extra energy that it gains has to go somewhere, and it does this by the spontaneous creation of a photon, which then goes traveling off on its own. So, charged particles, straight, don't lose energy. They lose energy at the very end of their path. Electrons, tortuous paths, they lose energy all the way along their paths, and they can produce this X-ray radiation from these Bremsstrahlung interactions. Now, photon interactions with matter, kind of three different ways: photoelectric, Compton, and pair production. Now, the photoelectric effect is when a photon comes in to the vicinity of an atom, a whole atom, not just the nucleus, and gets absorbed. Now, when we say gets absorbed, that means it basically just disappears and its energy is converted to excitation energy of the atom. Now, if it's sufficient enough given the type of atom, then this extra energy can be removed from the atom by it ejecting one of its electrons. Now, generally speaking, with photoelectric effect, the energies involved are pretty low. So this normally ejection of an electron does not result in a characteristic X-ray as further shells start fill in that vacancy. They're either pretty low. They can be in the visible spectrum. They can be I don't think they can be IR. Some of them can be UV. But we lose that incident. Photon, that incident high energy photon. It just goes away. Now, Compton scattering is the photon comes in, hits an electron, photon goes off in a different direction than which it came in, and then the electron gets scattered off in some related angle away from the point of impact. Now, the energy that can be transferred from the photon to the electron is governed by the Compton scattering equation, which is right here at the bottom of the screen. And it's determined by the initial energy that the photon has when it comes into the collision, which is the E, what angle it scatters off at, which is the theta, and then mc squared, which is the rest mass energy of an electron, which I showed in the earlier lesson when we started looking at the mass balancing, where I said, well, here's the mass of an electron, but we're not really going to use that. The rest mass portion or term of that expression that was on the slide is what would go in here. So the rest mass energy of an electron is 511 keV per c squared, or 0.511 MeV per c squared. So we can take the rest mass energy and we're basically converting that mass to energy so that we can directly do this computation. And the units line up because we're dividing energy, E, by energy, that mc squared. Okay, but for the most part, the takeaway here is the scattering angle and the initial energy are what determines how much energy is transferred from the incident photon to the electron. In pair production, I put it here for completeness. We're really not going to talk too much about this. It's actually quite an interesting reaction, which can only occur from a photon somewhere near the nucleus of an atom. And this is necessary basically to make the math work out, to provide the conservation of energy and momentum. The long and the short of it is, if a photon has a high enough energy, above 1.022 MeV, If it travels somewhere near a nucleus, it can spontaneously disappear and produce an electron and a positron. Now, any energy that they have over this, or that the incident photon has over this 1.022 MeV threshold, that becomes the kinetic energy, and it's distributed between the two particles that are created, a positron and electron. Now, the electron, it just goes off and does its own thing, probably going to get captured by a nucleus or by an atom at some point and become part of, a molecule or something. The positron, however, it's got a really brief life ahead of it. A positron, because it's the exact opposite charge of an electron, but in all other respects is exactly the same, can be called the antimatter counterpart to an electron. Now, what happens is when a positron and an electron come together, they annihilate, they disappear, and they produce two particular energy photons that travel in opposite directions away from the annihilation event. These annihilation photons can be called gammas. Some people who are very sticklers for correct nomenclature would say that they're not gammas, they're annihilation photons, whatevs. They have a very particular energy of 511 keV, which, surprise, is the same as the rest mass energy for an electron or a positron. Those two things, if a positron and an electron disappear, then we have to conserve that energy, so their rest mass energy is converted directly into photons. Now, photons interacting, we take all three of those different methods by which photons can interact, we sort of combine them all, and we come up with something called an attenuation coefficient. Now, there's two different types of attenuation coefficients that are part of this lesson. The first one is something called a linear attenuation coefficient, which assumes that this material that we're calculating it from is of a certain density, or this element is of a certain density. So that's why it just has one variable. And then we find with the thickness of whatever the material is, how many are going to be left after they go through this material. So the number that we start with, n naught, turns into the number that we end up with, which is just n, after traversing some x distance through a material. Now, the other attenuation coefficient is something called a mass attenuation coefficient. Now, it's pretty similar, but with one key difference. The linear attenuation coefficient, it assumes some nominal density of the material. Let's take, for instance, aluminum. Aluminum has a density of 2.17 grams per cubic centimeter. So if I were to look up aluminum linear attenuation coefficient, it would be based off of this density. Well, what happens if the aluminum is hot? Well, when things heat up, they tend to expand and become less dense. Well, crap, now I need some way to account for this when I'm looking at my photon calculations. And I use the mass attenuation coefficient in order to do this accounting. Now I can take and modify this pre-calculated value by whatever my actual material density is and still come up with the right answer. Now, on this particular illustration here, we have I naught photons per meter squared on one side, Ix photons per meter squared on the other side, some thickness x, and then we have some little infinitesimal element dx in the middle. And the reason it's shown this way is that these two expressions come from a differential equation, and it's summing over a bunch of these infinitesimal thicknesses dx. That's all that means. Now, what is I? Well, I stands for intensity. And intensity is simply the number of photons hitting this material per second. That's it. So they're pretty much interchangeable as far as these equations are concerned. If you're given a source of photons in terms of number per second, then you're calculating intensities. If you're just given total number of photons, then that's the equation that you see here on the screen. Now, if we put it all together, all these interactions together, and again, we come up with this overarching attenuation coefficient, we can look to see, which one of these makes up what percent of the photon interactions that are going to occur. So in this particular example, we're looking at photons interacting with air. Now, as photon energy starts at the very low end, basically it's being dominated by the photoelectric effect, which is that diagonal line that goes all the way up past 100 on the y-axis. So that means that at those low energies, the most probable thing that's going to occur is a photoelectric absorption. There's Rayleigh scattering in there. I know I didn't really talk about it because it's kind of weird. It's a coherent scattering where a scattering event occurs, but no energy really is lost. Again, it's kind of weird. It's not really important for our intents and purposes, but it's on there. Now, as we move up in energy, what we start to see is that Compton scattering, right around between 80 and 90 keV, Compton scattering starts to be the dominant effect for the interactions. And it continues on up into very high energies of 1 MeV all the way to 10 MeV. Now, you're probably asking yourself, well, where's the pair production? Well, pair production is a function of not only the photon energy, but the effective Z of the material that it's moving through. And air is composed a lot of low Z materials, hydrogen, oxygen, nitrogen. So the probability that one of these high energy photons is going to get somewhere near one of these nuclei in order for the pair production to happen, that in itself is very low. And then the probability that momentum transfer or interaction with a nucleus is going to occur at all, even if the photon's near it, that's also very low because of the number of nucleons, and it has to do with the quantum mechanical wave interactions between the photon and the nucleus. And you're probably falling asleep with that description, but that's really how it works. Because of that variation with energy and Z, or that probability change with Z and photon energy, for air, it doesn't really happen, therefore it's not really here. Now, finally, looking at neutron interactions. Neutrons really interact in 3 different ways: elastic scattering, inelastic scattering, and neutron capture. Now, elastic scattering is kind of like your classic billiard ball hitting each other and bouncing off in opposite directions. All the energy is conserved. There is no deformation, really, of the 2 things that are hitting each other. Inelastic scattering is a little bit different. Inelastic scattering is where the neutron hits the nucleus and it transfers some of its energy into internal energy of the nucleus, or an excited energy of the nucleus. And in like regular physics terms, you can think of it as if I hit a pool ball against another pool ball, they don't really change shape, right? So they just bounce off each other and that energy is conserved. However, if I, hit a pool ball into something like a beach ball, the beach ball is going to deform as the pool ball hits it. And some of that energy of the pool ball is going to be lost basically to heat of the deformation of the beach ball. That's kind of what an inelastic scattering is for neutrons. And then finally, we have neutron capture, which covers the whole range of interactions that can occur, where we have a neutron in and a gamma out, we have a neutron in and fission occurs, we have a neutron in and several other neutrons come out, or even a neutron comes in and an alpha particle comes out. Okay, these are all grouped under the category of neutron capture. So how do we figure out what's going to happen? With the photons, we had a nice expression with the attenuation coefficients that would tell us, over a certain amount of distance through a material, how many photons are going to interact. And then we could use those, the breakdown of the individual components of photoelectric effect, Compton scattering, and pair production. We can do kind of the same thing with neutrons, but we don't have attenuation coefficients with neutrons because, first of all, they only really interact with the nuclei. And we don't really want to call them attenuation coefficients because we're not interested in how many are interacting. We're more interested in what's the interaction. So in the lecture notes, I drew a parallel between the attenuation coefficients and cross sections. Now, cross sections can be thought of actually quite simply when you're thinking about a neutron and a nucleus. Now, if you take a neutron that's coming at a single nucleus, now in three-dimensional space, and we can assume very roughly that a nucleus is spherical. But if you're the neutron and you're flying at that nucleus, you don't see a sphere, you see a circle or a cross-sectional area of that sphere. And that's kind of what I'm trying to demonstrate here on this slide, is that, you know, when you're talking about a nucleus, or, well, for a photon, you know, an electron, but sort of not really. When you're looking at it from the incident particles point of view, all you see is that cross-sectional area. Now, is this really how it works? No. No, it's more of that quantum interaction that I talked about just briefly before. But it's a good enough approximation, right? It's something that you can wrap your head around, that the probability of interaction has to do with, you know, the size of the nucleus, if you will, or the cross-section of the nucleus, and that is a probability of the neutron hitting it. Again, not really how it works, but it's close enough. Now, this is a microscopic cross-section. That is the probability of a neutron hitting a nucleus. A macroscopic cross-section, however, is the probability of a neutron hitting a bunch of nuclei that are all within some volume. And the way that we do this is all we're doing is trying to find out how many nuclei are within that particular space. And we do this using Avogadro's number, which is 6.022 times 10 to the 22nd. So we use that with the atomic mass of whatever the nuclei are. So for like uranium, it would 238, it would be 238. For uranium, 235, 235, and so on and so forth. And then we're looking at the density of the material, because just like with the photon interactions, the density determines how many of those nuclei are going to be present within a certain volume. So when we put all that together, we can transform from a microscopic cross-section to a macroscopic cross-section, which is analogous to that linear attenuation coefficient. We don't need a separate one to account for the mass, because it's built in to that transformation from microscopic to macroscopic. Now, in the next lecture, we're going to put all this to use when we talk about fission, fusion, and chain reactions. So, until then.